Okay, boys and girls, as you can see, we're missing a lot of people, and I don't know how they're going to figure this stuff out on their own, but that's not really our issue. So we move on to, and I want you guys to know last year for the test, I also put lessons 3.7 and 3.8 on there. 3.7 is not going to be real difficult, but it is very, very new and can be confusing if you're not in class. 3.8 is going to take us a while. It's probably going to take us 4 days to get through. 3.9 is nice and quick. You will expect a test coming up before Christmas breaks. That means we have, we'll definitely within 3 weeks get through this material, and we'll move on to Chapter 4, which is really the heart of differential calculus. So, examples of explicit equations. Today, you are doing implicit differentiation. So, you know, the nice thing is that, you know, Ina's, their question was, you know, I don't know when to use the chain rule, the product rule, stuff like that. You will know when to use implicit differentiation. Here's where we use examples of explicit differentiation. Watch. Yes. Well, you're kind of already out there. So, all right. Y equals x squared plus 3. We can use explicit differentiation. F of x equals sine of pi x. Explicit differentiation. Whoop, nope. And then, for example, if we had y equals the square root of 2x minus 1, we could use explicit differentiation. We have been using explicit differentiation so far. Explicit is when y is solved for. The question is, we have lots of things that, you know, y is not solved for. So here's one example, and here's a classic one. X squared plus y squared is equal to 25. A for the day, what type of shape is that? Circle. We can find the instantaneous rate of change of a circle at any given point without even expressing it as a function, which is cool. Because before we had to use, you know, we had to use something that only related to functions. Well, that's not the case in this scenario. Here's another example. What if you had this? X over y plus y squared minus 2x is equal to 15y. Now, that's a challenging problem to be able to find the derivative at a given point. But you can see examples of implicit equations. Ben Jones asks a good question. He says, can't we just solve for it? Well, yeah. But, again, it's kind of like, you know, do you want to go through life with a hammer or an ear nailer? And you're... All right, okay. There are times where you can solve for y and go from there. But that's not always the case. Okay. Let me help you understand a little bit of what happens here. Okay. F prime of x, what does that mean? That means the derivative of the function. D over dx, it means the derivative, but derivative with respect to x. dy over dx means derivative of y with respect to x. Something is going to happen here in a second that will blow your brain. And then you'll just have to say, okay, I'm going to accept it, and we're going to move forward, okay? Watch. Don't write this down, but just watch. Y equals 2x plus 3. We want to take the derivative of it. What's the derivative of 3? What's the derivative of 2x? 2. What's the derivative of y? Okay, interesting. People say 1, and people say y prime. The derivative of y with respect to y, if y was our variable of choice, we would say it's 1. But the variable that we're taking the derivative with respect to is x. So here's actually what we do. The derivative of y is 1, but we have to attach on a y prime. So therefore you get y prime is equal to 2. I'm just going to switch this just to a very basic example. Watch. I'm going to take that equation. I'm going to multiply through by 2. And I'm going to get 2y is equal to 4x plus 3. Watch this. What? Plus 6. What's the derivative? What's the derivative of 6? 0. What's the derivative of 4x? What's the derivative of 2y? You would say 2, but then you realize that we have to attach a y prime because y prime indicates that we were taking the derivative with respect to x. When I solve for this, I get y prime is equal to 2. See how they are the same? So my point is that you don't have to solve for y in order to do it. So let's do the very basic example given right here. Find the derivative of the circle x squared plus y squared equals 36 using implicit differentiation. Here's what we do. What is the derivative of x squared? 2x. Actually, I'll write it all out, okay? This is what we're doing. We're taking the derivative with respect to x. The derivative of x squared with respect to x is just 2x. The derivative of y squared is 2y prime. But since it was with respect to x, I have to attach a y prime. You could also write that as dy over dx. That's what it means. Y prime is dy over dx. The idea is that we're taking the derivative of something that was different than the variable that we're taking it with respect to. And anytime we do that, we have to attach a y prime. What's the derivative of 36? 0. And you'd have 0 times, yeah, and it would just go away, so you get 0. So we want to solve for y prime here. How do you solve for y prime? So y prime times 2y is equal to negative 2x. Now what? Divide by 2y. And you get y prime is equal to negative x divided by y. That's it. So the idea is that if you want to know the instantaneous rate of change now, you need both an x value and you need a y value. You find then the y value. Okay? So let's do an example on the back side, then we'll go back here and we'll write the summary. Okay? It says use implicit differentiation to find the derivatives of the following equations. What is the derivative of 3x squared? 6x. What's the derivative of negative 4y? Negative 4, and you attach a y prime to it. Anytime you take the derivative of y, you have to attach a y prime. equals, what's the derivative of 4x? 4. Now what? Subtract the 6x. And I get negative 4y equals 4 minus 6x. Now what? And I get y prime is equal to, will be a positive 3x minus 2 over 2. Yes? No? So I factored out a 2 on the top and a 2 on the bottom. I factored a negative 2 on the top and negative 2 on the bottom. Yep. Okay. Let's try B. Y to the third minus 5x plus 2y equals 3x plus 1. A little bit trickier here. 3y squared y prime. What's different about this situation? You have 2y primes. How do I handle that? Subtract and factor that. Very good. So we're going to leave everything with y prime on one side. Everything that doesn't have a y prime will go on the other side. So I have 3y squared times y prime. I'm going to leave that. And I'm going to leave the plus 2y prime. I'm going to take this minus 5 and move it over to get a positive 8. Now, taking Andrew's advice, I'm now going to factor out a y prime. That way, it is solved for. Okay? It's isolated. I'm left with 3y squared plus 2 is equal to 8. And now I divide both sides by 3y squared plus 2. I get y prime is equal to 8 over 3y squared plus 2. So let's go back and write our summary of what to do. What to do. In summary, in order to find a derivative of y with respect to x, first of all, take the derivative. With respect to x. Remember to attach y primes. After we take the derivative and we attach our y primes, what do we do next? Gather only y primes on one side. After we gather the y primes on one side, what do we do? Factor out y prime, then divide. Divide and solve. And that's what we do. So, let's try the rest of these examples. What's the derivative of x? 1. What's the derivative of 2y squared? 4y y prime. That's the most important thing you remember today, is that when you take the derivative of y squared with respect to x, it's 4y y prime. Doesn't matter. I'm just not being consistent. You can leave the y prime in front or in back. Multiplication is commutative, so you can move it around however you want. Equals, what's the derivative of 3x to the third? 9x squared. Why don't I have to attach a y prime there? Because you're taking the derivative with respect to x. Very good. Plus, what? 16 y to the third times y prime. Now what? Gather all my y primes over on one side. Factor out y prime times 4y minus 16y to the third equals 9x squared minus 1. Divide. Question. It's often that your answers will differ by a factor of -1 on the top and the bottom. So, for example, Ben got 1 minus 9x squared over 16y to the third minus 4y. That all just has to do with whether you moved your y primes to the left or the right. So it's okay to differ by a factor of -1 on the top and the bottom. It's essentially the same. Yep. For consistency, I tend to move the y primes to the left-hand side. Okay. D, little bit more difficult. Does anybody recognize what makes this problem unique? Okay, sometimes people shout stuff and it's all the same thing. You're like, wow, my class is really on the same page. We must be doing something right. That was gibberish. What what makes this unique? Product rule. Look. The 3xy. That requires that I use the product rule. Because you have x times y. So, let's do the first part. What's the derivative of 5y squared? y prime equals, what's the derivative of 9x? 9. So let's do this first part now. I have 3x and I have y. I have 3x and I have y. And I want to take the derivative of that with respect to x. So I'm going to break it up into two pieces. I have 3x and I have y. What's the derivative of 3x? 3 times y plus, what's the derivative of y? Y prime times 3x. So that's my derivative. I just did the product rule. That's it. You want to see this? Okay, what's the derivative of 3x? 3 times that left alone, plus the derivative of y, which is y prime, times that left alone, 3x. And so there you have that. So now what I'll do is, as I go back to this page, now I've got my equation. I now need to solve for y prime. I'm going to gather my y primes on the right or left-hand side. So I have y prime times 3x minus 10y y prime is equal to -9 minus 3y. Factor out my y prime, and I'm left with 3x minus 10y is equal to -9 minus 3y. Divide by y prime, or divide by 3x minus 10y, you get y prime is equal to -9 minus 3y over 3x minus 10y. So, a good friend of ours named Ben Jones started the class by saying, why not always just solve for y? good luck at looking at example C and solving for y ahead of time and not using implicit differentiation. I think that you'll find it extremely, extremely difficult. It might take me the better part of a day to do that. So, anyway, all right. As you know, our class started with this single question: write an equation for a line tangent, and that's where we always come back to, given any type of problem. No issues here. We have a point. Does this point lie on this circle? If you plug in -3 for x and 4 for y, do you get 25? You sure do. So we can write an equation for a line tangent at that given point. All I need to do is find the derivative and plug in my point. In order to write an equation for a line, I need two things. What are they? Slope and a point on my line, which is -3, 4. In order to find the slope, I need to take the derivative. What is the derivative of x squared? 2x. What's the derivative of y squared? Equals 0. Subtract the 2x. 2y, y prime is equal to -2x. Divide by 2y, y prime is equal to -x over y. So that means that the derivative of y with respect to x is -x over y. So I plug in my point. If I plug in -3, 4, I get what? 3/4. The derivative of 25 is 0. Mark asked a really good question, guys. He said, do you ignore the 25? The most common mistake I remember from this test is that when people would not take the derivative of that. They would not get 0. They would just leave it as 25. The derivative of that constant, remember, is 0. Because I plug in the -3, 4. -3 for x and +4 for y, I get 3/4. Now I could write my equation. Y, 4, is equal to m, 3/4, times x, -3, plus b. We're going to turn it to common denominator. 16 over 4 equals -9 over 4 plus b. Add the 9/4, I get 25/4 is equal to b. My equation for my line, y equals 3/4 x plus 25 over 4. And if you draw your circle, you'll be able to tell that that does in fact work out. I could. I don't want to show off. Kyle, I look good in everything I wear. Would you like me to wear a tighter shirt? You're the one bringing it up. What? Can you tell me the derivative of secant? Sticks and stones may break my bones, but words will never hurt me, Devin. All right. All right. So, Andrew is correct that you can use the chain rule for that one. You can use the chain rule. Anybody know what shape that is? This is a hyperbola. And if you were to graph a hyperbola, again, it's pretty amazing we can find the derivative of it. I'm not going to use, I'm going to work with Ina here. I'm going to work with Ina and say we are not going to use the chain rule. If you don't want to use the chain rule, just square it all out. No big deal. Okay? So I have 1 over 18 times, what is y minus 4 quantity squared? Because I'm dividing by 18. Minus 1 over 4 times no, you very much cannot. Okay, I'll show you one time here, okay? You ready? Ready, Ina? I'm just saying, watch, okay? 25, okay, minus 16 is equal to 9. Yes? You want to square root both sides. So I would get, what, 3? What's 25? Minus 16? 9. So you get square root of 9, which is 3. That's because I took the square root of the whole thing. What you want to do is you want to do this. You want to take square root of each part. You can't take square root of parts. You get 5 minus 4. That's not 3, so it doesn't work. Okay. All right. So constants. Constants just come along for the ride. You don't have to worry about this 1 over 18. It will just always be there. We'll make use of it later on. What's the derivative of y squared? 2y times y prime. What's the derivative of negative 8y? Negative 8y prime. What's the derivative of 16? 0. Minus, what's the derivative of x squared? 2x. What's the derivative of 2x? Equals 0. So, I'm going to multiply through my fractions, okay? So that we can, we'll have y times y prime over 9 minus 4y prime over 9 minus x over 2 I just distributed my 1 over 18. I distributed my negative 1/4. I need to make sure I have all my y primes on one side, correct? Oh, yep, thank you. So we gather those other terms on the other side. I have y times y prime over 9. It doesn't matter, it's multiplication. Minus 4y prime over 9. Sure. Equals x over 2 plus 1/2. So all I did is I moved my minus x over 2 and my minus 1/2 over the other side. I'm just following those same steps that we laid out in summary of how to use implicit differentiation. Sure. X plus 1 over 2 would be fine. Now I need to factor out a y prime. And you'll end up with y prime times, looks like I have y minus 4 over 9, right? Equals, we'll take Jalen's advice, we'll go x plus 1 over 2. I want to get rid of it, so I'll multiply by the reciprocal. So I'll get y prime is equal to, looks like I'll have a 9 times x plus 1 on top and a 2 times y minus 4 on bottom. What is my ultimate goal? To write an equation for a line tangent at a given point. What is my point? Negative 310. What is my slope? How do I figure that out? I plug it in. So I have negative 3 for x. I have 10 for y. So if I plug in negative 3 for x, I have negative 3 plus 1 is negative 2 times 9 is negative 18 over, let's plug in 10 for y. 10 minus 6 is, or 10 minus 4 is times 2. Negative 18 over 12 is negative 3 halves. So we just figured out that the slope of the line tangent to that hyperbola at point negative 310 is negative 3 halves. In order to solve this, y equals m times x plus b. 10 equals 9 over 2 plus b, or 20 over 2 equals 9 over 2 plus b. Attach a separate sheet of paper. 11 over 2 equals b, so we have y equals negative 3 halves x plus 11 over 2. That's the equation for the line tangent. Now, once again, you got to pause every once in a while and say to yourself, if you started out with that problem at the beginning of calculus where you were to try to find a line tangent to a hyperbola at a given point, you would say, no way, that seems nearly impossible. Now, I know it took us a while, but you could do that problem in 5 minutes. No problems. All right, your assignment, you guys got a few minutes now, but you're going to have tomorrow to work on this assignment in class as well, because half the class is missing, and I'm going to have to redo instruction anyway. So, for all our YouTube watchers, there's your assignment. Good luck. Hope the blood drive went well.